Hello, my name is Evan Wardell, and in this video I'm going to be talking about a system for harmony tracking musical sound design which I've created within a remake of the game Breakout, first using only Unity and C# scripts, then replicating and expanding upon the system using Wwise. I'll talk a bit about the process, including a look at some C# scripts and the Wwise editor. I'll also be touching upon some of the approaches taken with the non-musical sound design in this project, which combines with this system to produce the full mix. But before I go any further, I'd like to show a quick, full playthrough of the game to provide some context for the rest of the video. Now, before getting too much into how this all works in terms of implementation, I wanted to talk a bit more about what you just heard and the design philosophy behind it. Essentially, my goal was to create a system for pitched sound effects which accomplished two things. One, I wanted them to follow and emphasize the harmony of the background music, including both changes to the current chord and modulations to different keys altogether. Two, I wanted them to have an overall random and variable character for extended play, while also taking on a more satisfying sense of order in response to the player doing well. That is, when the player hits multiple bricks in sequence before the ball comes back down to the paddle. Based on the first of these criteria, I wanted to scope the background music itself as a sort of minimum viable product, which features basic shifts in harmony and key, but only enough to design the system around, without generating too much repetitive work. Given this, the harmony is limited to 4 open fifth dyads within the B-flat major pentatonic scale, centered around F in order to achieve a bit more ambiguity, with a short section at the end modulating instead to 2 such chords within the D-flat major pentatonic scale, before coming back to B-flat. This allows us to limit the system to 2 scales over the entire track, with only 6 possible roots total to be emphasized. With this system in place, then, I separated the main pitched content into 2 main sources, the paddle and the bricks. For the paddle, the idea was simple. Just play the root note of whatever dyad is currently playing, clearly emphasizing and grounding the harmony to an action which is frequent, but not too frequent. For the sound of the ball hitting the bricks, my specific goal was a bit more complicated. While I was able to limit their notes to only 2 octaves within 2 scales, varying only by key and not by each chord, I didn't want to only have these notes follow one particular sequence every time, as it would have been tediously repetitive to listen to over extended play. However, I also didn't want to simply play from among these notes at random, as I wanted to give the player a sense of satisfaction and reward when hitting multiple bricks in sequence. Given this, I opted to instead create a hybrid approach, where the first brick hit after touching the paddle will play randomly from the first 4 notes of the scale, then progressing continuously upward through the scale until the top, at which point it once again repeats the last 5 notes. This entire system, then, is reset every time the ball once again hits the paddle or falls outside the play area, leaving the scale to start back up again from one of those first 4 pitches. Now, let's take a look at how this was done within the code and the Wwise project. As I mentioned earlier, I'd originally implemented this solely using Unity and C# scripts, and while the current version is the one which integrates Wwise, I thought it might be interesting to show what the Unity-only integration looks like, both as an example of what can be done through code alone, and as an example of what Wwise makes easier to accomplish, as well as what adjustments may need to be made in order to allow for the same degree of customization. The first thing I did was create 2 enums, one to store the value of the root of the current chord, and one for the current overall scale being used. I then set up the start function to find the length of the audio clip for the loop portion of the music, hardcode the expected number of measures, and then use both of these to find the time value of each bar line, storing each of these within a measures array. Then, within the update function, things get a bit messy. I first check whether the music intro segment is currently playing, in which case I set the enums to the root and scale values for that part of the music. Otherwise, I find the time value at which the loop segment is currently playing, and then compare this against the measures array we generated earlier, starting from the end. If the current time is greater than the time at which the 20-second measure starts, I set the root and scale to the appropriate values for those last two measures. Otherwise, if the current time is greater than the time at which the 18th measure starts, I do the same for the harmony during this section in between, and so on and so forth. This structure represents the entirety of how I originally tracked the harmony of the music. With these enum values set to change with the root and key of the music, I'm now able to use them to dictate what notes are played according to the system which I described earlier. As you can see in the paddle sound function, each time the paddle is hit, I check for the current root, and then based on this, play the corresponding note from its designated audio clips array. Moving to the brick sound function, the requirements for enum access are even simpler, as we are only discerning between two possible scales from which to play the notes. The complexity of this function, then, comes from the hybrid random then sequence approach to playing notes in the scale which I discussed earlier, implemented here using a brick tracker value, used as an index when selecting which clip or note to play. If the paddle has been hit more recently than the last brick, this will be set to a random value between the first note in the array and the fifth to last one. Otherwise, this value will be incremented by 1 each time another brick is hit, until it reaches the end of the array, at which point it will return to the fifth to last value. Using this value, the function then plays a note from the audio clip array corresponding to the current scale. Finally, it sets the value of hit paddle to false, ensuring that this incrementation process will continue until the next time the paddle is hit. As one quick last note on the script, you may have noticed earlier that the brick tracker integer is also manipulated at a few points within the update function. This is because the notes in each scale aren't always directly above or below one another according to index number. Given this, I've taken the points at which the scale enum changes, and changed the brick tracker's value such that the note being played will still continuously increment upward during a key change. Of course, this entire setup could certainly be further optimized, even beyond the low-hanging fruit, like opening hard-coded variables to the Unity inspector, converting structures to switch statements, and separating repetitive actions into dedicated functions. But even if these optimizations were made, the process of making changes and implementing the system within different contexts would still be a fairly complex and tedious one. So now, I'd like to take a look at the most recent version in which Wwise is implemented, and show how this streamlines the process. Looking at the same script in this more recent version, we can see that it has been cleaned up considerably. For starters, we can see that there is no longer any update function, as the entire process of tracking harmony has been offloaded to Wwise. Most other functionality has also been replaced by Wwise event calls, with the exception of some logic within the brick sound function, which I'll get back to later. Switching over to the Wwise project, let's first take a look at how harmony tracking has been implemented. If we look at the intro and loop segments for the background music within the interactive music hierarchy, we can see that they are populated with a variety of event queues. If we look at one of these events, we can see that all it's doing is setting two states, one for the root of the current chord, and one for the associated central key. These states are then used in the same way as the enums from the Unity-only implementation. As we can see with the paddle hit blend container, its pitched sound effects are organized within a switch container. This container is then assigned to use the root state group, and each individual note's sound SFX object is assigned to the corresponding state. So, each time the paddle is hit, Wwise will simply check the state that was last set by the event queues in the background music, and then tell this switch group to play the corresponding note. We can also see that the musical victory and game over sound effects follow the same logic using the key state group. The brick pitched sounds function somewhat similarly, except that there's once again an added layer of complexity. If we expand the F switch container, we can see that it contains 4 separate sound SFX objects, as well as a sequence container. If we expand this sequence container, we can see that it contains the last 5 notes of the scale. So, why is it set up this way? Well, while the random and sequence containers in Wwise are very powerful, there isn't actually any way to use them exclusively to recreate the same sequencing behavior as we had before, as a Wwise authoring application does not allow you to randomly select a starting point for a sequence container. Given this, I needed to instead use a switch container, along with a switch being randomly set within a C# script in Unity. Looking back at that script's brick sound function, we can see that some of the previous brick tracker manipulation has been preserved. As before, if the paddle has been hit more recently than the last brick, the value is set to a random integer between 0 and 4. Otherwise, it will similarly continue to increment, this time until it reaches 4, at which point it will stay at 4 until the next time the paddle is hit. This value is then used to set the value of a numBrick RTPC within Wwise. Looking back at the Wwise editor, we can see that this numBrick RTPC is used to set the value of a bricks hit switch group. This switch group, in turn, is then used to determine what will be played by the respective brick-pitched switch container for each scale. As you can see in the F switch container, these 4 sound SFX objects and the sequence container containing the last 5 notes are each assigned to a different switch value. If you're familiar with how sequence containers work within Wwise, you can probably see now why I've arranged this switch group to only have 5 switches. Rather than continuously increment the numBrick RTPC until the end of the scale, then bringing it down to repeat the last 5 notes, I can instead just set the sequence container to restart at the end of the playlist, easily recreating the same functionality. Finally, in order to ensure that those sequence containers always progress correctly from the previous 4 notes, I've created a reset playlist event which returns them to their starting notes, which is then called from the game code when the ball hits a paddle or exits a play area, or when the game is otherwise restarted. As one final note on the Wwise project, you can see in the actor-mixer hierarchy that the Wwise authoring environment has also enabled me to easily combine the non-musical sound design with these systems. Among other things, this includes random step containers for the non-pitched sound effects in the brick hit and paddle hit blend containers, separate random step containers for the wall hit and ball throw sounds, a blend container of looping sound effects for the paddle movement sound, fading in and out based on a paddle speed RTPC being sent from the game, and the ability to slightly pan some of these sounds left or right based on their position on the screen, also through an RTPC being set via the game code. Well, that's all I wanted to talk about for this project. Hopefully you can see that, while it still requires some code for certain custom functionality, Wwise has many features which make it much easier to create this kind of musical sound design. In particular, event queues within the interactive music hierarchy make it incredibly simple to track harmony. At any rate, thanks so much for watching. As always, please feel free to reach out or leave a comment if you have any questions or feedback, as while this wasn't meant as an in-depth tutorial on how to create each feature, I'm more than happy to clarify certain parts in case anybody wants to learn more about C# scripting or Wwise implementation, or is having issues doing something similar. Anyways, thanks again, and I'll see you next time.